Welcome back to the Advanced Microcontroller series. In today's session, let us discuss about communication protocols. And here is the agenda: introduction, modes of communication, types of communication and protocol. And this is the introduction of communication. Communication is the exchange of data between two or more devices using a defined communication protocol. Simply, we can say that it is the exchange of information between two parties. But why do we need of communication? So, why do we communicate? Because we need of it, isn't it? But what about system? Why do system communicate? Is communication required between the systems? So, let me consider one example. Suppose now we are designing an automatic school bell system. So, for that, what is the requirement? We have microcontroller that should ring the bell every morning at 9 a.m. So, for this purpose, here we using one timer. So, this timer will help us to know whether it is 9 a.m. or not. And so now what will happen? This microcontroller keep running all day just to check whether it is 9 a.m. or not. So it will consume unnecessary power. So if the system runs on a backup battery, so here we having one more battery which is connected to this microcontroller. So what will happen? The battery will drain quickly, isn't it? If it runs all day just to check whether it is 9 a.m. or not. So to avoid this problem, we use an RTC. So what do you mean by RTC? So RTC is nothing but real time clock. So RTC is nothing but real time clock which has its own coin cell battery and consume very little current. So now assume the microcontroller is in sleep mode. The microcontroller is sleeping. So since microcontroller sleeping, right? So who keeps track of the time? RTC. So at exactly 9 a.m. the RTC generates an interrupt. So the interrupt wakes up the microcontroller. So the microcontroller receives the interrupt, turns on the relay connected to the school bell, rings it for 10 seconds and then goes back to sleep. So here RTC and microcontroller. So here here RTC and microcontroller. So both are communicating. So how it's communicating? RTC tells the MCU. RTC tells the microcontroller it's 9 a.m. wake up, and this microcontroller performs the action. So this is the example. This is the reason the communication is required between the systems. And next is the modes of communication. So here we having simplex. So what do you mean by simplex? That is the one-way communication. So if communication happens in one direction, or one-way communication is nothing but simplex. So here data flows in one direction only. So for example, radio, TV, keyboard. So here keyboard to computer, which computer using keyboard, isn't it? So that's one. So here why it is one-way communication? Because so assume radio or TV. So we are just listening, isn't it? So that's why it is one-way communication. So next is the half duplex. It is two-way communication but one at a time. So here both devices can send and receive but not simultaneously. So one party communicate at a time. So that is nothing but the half duplex. So for example, walkie-talkie. So if one person is speaking, the other one listen, isn't it? If other one wants to speak, then he should press some button, then he can speak, and opposite party just listen. So at a time both person is not able to speak, isn't it? Simultaneously they are not able to speak. They don't have option like that. But in full duplex communication, that is two-way simultaneously, both devices send and receive at the same time. So here both parties can communicate simultaneously. For example, mobile phone call. So you can talk and opposite party also talk. There is no restriction like half duplex, isn't it? So this is what full duplex. So this is the modes of communication, and next is the types of communication. Serial parallel communication. So in case of serial communication, how many bits are getting transmitted? One bit at a time, isn't it? So data is transmitted one bit at a time over a single communication lines. So it is bit by bit communication. But in case of parallel communication, multiple bits are transmitted simultaneously using multiple data lines. But in case of serial communication, it is a bit by bit communication. For example, UART, SPI, I2C and CAN protocol. So these are the example protocols. All example protocols comes under serial communication. So we are more concerned about form factor. So form factor means what? If I using parallel communication, then don't you think number of lines are going to more? So here you can see what is parallel communication. Multiple bits are transmitted simultaneously using multiple data lines. So let's say, we can say that parallel communication is nothing but n. So instead of saying multiple bits, we can say that n bits are transmitted using the n data lines. So now my n value is 8 bit. Now 8 bits are getting transmitted for instant. Then what happened on my hardware? At least I need 8 lines, isn't it? So here number of wires are high. That's why people are going with the serial communication protocol, not parallel communication protocol. And serial communication protocols are most dominated protocol. So in this series we discussing about the serial protocol, not parallel, and also these are the wired protocol. So what are the serial communication protocol? I already told, right? UART protocol, SPI, I2C and CAN. So people are concentrating too much on serial protocol. So nowadays this protocol is faster. So compared to the parallel, serial communication protocols are slower and parallel communication protocols is faster. But nowadays what happened, people are concentrating too much on serial protocol, right? So nowadays this protocol also faster. So this is the type of communication. So another type is synchronous asynchronous communication. So what do you mean by synchronous? So here communication happened with respect to clock pulse. Bit is getting transmitted. For every clock pulse, bit is getting transmitted. Sender and receiver share a common clock here in case of synchronous. But in case of asynchronous communication, there is no clock lines. So communication happens with respect to trigger. First it has to generate trigger and get the attention of receiver, and then communication will happen. So each data packet or frame contains start and stop bits to indicate its boundaries. So this is about the asynchronous communication. And next is the protocol. So what do you mean by protocol? A set of rules and standards that define how two or more devices communicate and exchange data correctly. So protocol is nothing but rules. So these rules include how two or more devices communicate and exchange data correctly. So imagine there are no traffic rules. Then what will happen? Some vehicles drive on the left, others drive on the right, some ignore red lights. There would be accidents and confusions. So traffic rules are the protocol which everyone follows, isn't it? So like that, here also we having some protocol. So coming to system have to talk with each other using pulses or signals. So those pulses, those signals has to be interpreted on common platform, and there should be some rules for how to send signal, how to receive signal. That's why we having protocol. So following the protocol, communication is reliable, right? That's why there is a need to follow the protocol. So who created this protocol? Some companies created a protocol, and that is famous. That's so we having protocols. Your protocol. So this is developed by the Intel company, and SPI protocol is developed by Motorola, and I2C developed by Philips, and this CAN protocol is developed by Robert Bosch. So these are the company which developed protocol, and that's nothing but this one. This list is nothing but that protocols. So now let us talk about protocol. Before that, let's discuss about the interboard protocol and intraboard protocol. So what do you mean by interboard protocol? So assume, so okay, let me draw. So here we having two boards. So let me discuss about the interboard protocol. So what are the examples for interboard protocol? So interboard protocol. So example protocols are UART protocol and one more example sir CAN. So this comes under this interboard protocol. So if communication happens between two different boards, so here we having two different boards, right? So this is PCB1 and this is PCB2. Both are the boards. So here what will happen? So the communication happens between two different boards by using a protocol. Then it is what? Interboard protocol. So this is the example. So you can communicate between two boards or systems by using this protocol. And what do you mean by intraboard protocol? So we had two types, isn't it? One is the interboard protocol and one more is the intraboard protocol. So what do you mean by intraboard protocol? So for this also let me consider. So let me consider one example. So here we having, okay, let me erase both and I'll draw again. So here we having two chips or ICs. So let me label first. So this is chip 1 and this is chip 2. So what will happen in this case? Here, yeah, before that let me draw one board. So these chips comes inside the board, isn't it? So here we having two chips and this is what? PCB. So this is PCB board. So now on a single board, if you are communicating between two different chips, between two different ICs, then it is nothing but intraboard protocol. For example, SPI, I2C, these are the intraboard protocols. So now we having PIC microcontroller, isn't it? So PICSimLab, yeah. So here we having board. Now if you want to communicate between two boards, in that time we use SPI or I2C. But if you want to communicate between two boards, then you can use UART and CAN protocol. If you want to communicate between two chips, then you can use the SPI and I2C. So in this case, in the PICSimLab, so whether it is intraboard protocol or interboard protocol. So here you can see chips are there, isn't it? So this is what? Nothing but the intraboard protocol. Here you can see PIC16F877A, this one, and here we having RTC. So now both are communicating. Let's assume both are communicating. Then it is nothing but the intraboard communication protocol, isn't it? And also here we having one more chip. Like that we having chips, isn't it? So this is what intraboard protocol. This is the example for intraboard protocol. Yeah, we had two types. So that's all about the introduction of communication protocols. And next is nothing but UART protocol. So I'm not going to explain much. So let's see the introduction of UART protocol now. So what are the agenda? Introduction, interface, hardware configuration and frame format. So in this protocol, no common clock is shared between the transmitter and receiver. So this is which type protocol? Synchronous or asynchronous? What do you mean? What stands for UART? Universal asynchronous receiver and transmitter. So this protocol is developed by the company Intel. So this is not synchronous, right? So there is no common clock is shared between the transmitter and receiver. And it stands for, yeah, that's what I said. So one more protocol we having. So this is what universal UART means, universal asynchronous receiver transmitter. One more type we having, that is nothing but UART, universal synchronous asynchronous receiver transmitter. So by using this protocol we can communicate both modes, synchronous and asynchronous, but only one mode you can see at a time. So this is what UART protocol. Now let's discuss about the UART protocol, universal asynchronous receiver transmitter protocol. So both devices must be configured with the same baud rate. So here in this both receiver and transmitter must be configured with the same baud rate. Data frames include start bit, data bits, optional parity bit and stop bit. So it is an asynchronous communication protocol and it supports duplex any. So it supports any type of duplex. So it supports simplex, half duplex and full duplex. And master and slave, we don't refer the term master and slave. Instead of that we refer host and device. Host means what? Host is the one which is going to control the device by sending all the commands. Usually this protocol is used for point-to-point communication. We can use any duplex for full duplex. So for example, you can use full duplex, half duplex and simplex. So how many lines are required for full duplex? Full duplex is two-way communication, right? So we need two lines. So via one line we can transmit and via another line we can receive. So here you can see the hardware configuration. So here we have in two lines, right? Via one line we can transmit and via another line we can receive. See, these are the two interfaces. So one is the receiver and one is the transmitter. So RX stands for receive. So it is the pin used to receive the data from another device. And one device is connected to the so receiver is the pin of one device is connected to the transmitter pin of the other device. So here we having two devices, right? So here receiver is the pin of one device which is connected to the transmitter. So here you can see, which is connected to the transmitter of the pin of another device. And transmitter, so what it will do means it uses to send the data to another device. Same transmitter pin of one device which is used to connect the receiver of the another device. Same thing. So we having two devices in this example. So in device 1 we having line 1, and in device 2 also we having, but in this is what? Transmitting. This line is, why this line is used? Because it transmits, right? Transmitting. And here this line is receiving. Here it is receiving, but here it is transmitting. Here it is receiving. Apart from this, there is one more common line is there. So here we having one more common line which is connected to ground. So this is what? Ground. And next is the frame format. So in UART communication happens between boards. We discussed in the introduction, right? So here assume here we having two devices. So UART communication happens between the boards. So what will happen? So device 1 wanted to transmit some data to device 2. Now let's take example of data. So assume our data is equals to 0x15. So this is the data. So binary of 0x15 is how much? 0001, right? 1 means 0001, 5 means 0101. So here we having MSB bit and LSB bit, right? So this D7 is the, so which is MSB bit and which is the LSB bit? So this is D7. So this is what? MSB bit, and here we having D0, that is what? LSB bit. So we having 2 bits. So device 1 wanted to transmit some data to device 2. So UART is a serial communication protocol. So in serial communication protocol, how communication happens? Bit by bit, right? First we communicating D0, then D1, then D2, like this. So it will keep transmitting data. So when device 1 transmitting data, in that time what is this device 2 doing? So what it is doing means sleeping? No, it is going to receive that data. So if it is sleeping, what will happen? Obviously it is not going to receive the data, isn't it? So don't you think before starting communication, so this is asynchronous, right? There is no clock line also. So it having, before starting communication, you have to get the attention of receiver, isn't it? So for that purpose we having one first bit, so which is going to transmit. So the first bit we are using is nothing but the start bit. So for that purpose we having one bit, that is first bit, that is what? Start bit, that is 0. So now device 2 understand, when it transmit to device 2 understand somebody starts communication, I need to pay attention. So when it receive the start bit, it understands. So start bit is transmitted. After that it start transmitting the data. So here we having data D0 to D7, right? So data will transmitted from LSB. So LSB is D0. So now data transmitted from LSB. So that is D0. Then D1. Then D2. Then D3. D4. D5. D6. D7. So like this way, one bit is transmitting at a time. And what will happen in this receiver? It receives the data, isn't it? Same thing it receives. First it received D0, then D1, then D2, D3, D4, D5, D6, D7. Like this it received 8 bits. After this transmit, this device 1 is having any another data to transmit? No, right? We having only this much, D0 to D7. Now, don't you think once you done, you have to tell device 2, I am done. You have to tell. How to tell? You have to send a stop bit. For that purpose, we having stop bit. So now device 1 needs to send a stop bit. So here stop bit. So stop bits are 2 bit, which is nothing but 1 1. So as soon as receive stop bit, so here it is sending, right? So here there is no space, that's why I written here stop bit. Okay, so here it receives the stop bits. So now this device 2 will understand I got the complete data. But how this device 2 will conclude when so whatever data I received, that is correct data or not, whether it is correct data or corrupted data, how it will conclude? So for that, actually in the frame we have one more bit. That bit is nothing but the parity bit. So this parity bit comes under D7. So after sending, so where is my cursor? Sorry. So after sending this D7, we have one parity bit. So let me write this stop bit here. So let me write here, okay? Please. So sorry, there is no space, that's why I am writing here. So after the D7 we having parity bit. So what do you mean by parity bit? So what do you mean by parity bit? So okay, let me explain what is the parity bit. So the device 1 is based on the so this device 1 is based on the data and calculate the parity and transmit. So what do you mean by parity? We are talking, right? So we are discussing about the parity. So you having two types of parity. So in the parity bit we having two types. One is odd parity and one more is the even parity. So what do you mean by odd parity and what do you mean by even parity? So now whatever data you transmitting, you count the number of ones. So here we having data. We transmitting this data, right? 0x15. So you need to count the number of ones. So here 1, 2, 3. So if the number of ones are odd, you can say that is odd parity. If the number of ones are even, then you can say that is even parity. So if number of ones are odd, then you can say that P equals to 1. If number of ones are even, then you can say P equals to 0. So in this case, what is parity? So how many ones are we having? 3, isn't it? So this is odd parity or even parity? It is odd parity. We have to write P equals to 1. So it is, so here it will transmit 1. So parity is what? 1. How this device to use parity bit for data integrity on arrival of data? So here on arrival of data, the way transmitter calculate the parity bit, the same way receiver also calculate the parity bit. If that parity bit matches with the received parity bit, then it will conclude that data is correct. Otherwise it will say I got the corrupted data. So in transmitter and receiver both having the parity bit. That's how data integrity achieved by using the parity bit. So whatever communication. So before that we discussed earlier, data frames include start bit, data bit, optional parity bit and stop bit. Now you got right? Yeah. So the same thing here, you can see parity could be either 0 or 1 bit and stop bits could be 2 bits, right? So that is what 1 1 and start bit is 0. And here we having D0 to D7 data. This is the start bit and this is parity bit and this is the stop bit. Data part can be 5, minimum is 5 and maximum is 9 bits. So here initially you want to do, so here initially the signal you have to change from high to low. Okay, so that is nothing but start bit is 0 and this one is the data bit and next is the parity bit and next is the stop bit. And here I said data part can be 5 to 9 bits. So in our example we had 9 bit. So if you are transmitting 9 bit, then you have to compromise with the parity bit. Instead of parity bit, use 9th bit. So here we having parity bit, right? So after the D7, so instead of this you have to use D8. 9th bit you have to use here instead of the parity bit. So, and next is the baud rate. So this one let's discuss in the next session. So that's all about the today's session. Thank you all.